We are now going to practice a small tutorial on the compressor section based on the detailed understanding that we have gathered together, right? And this will include some detailed section on velocity triangles also, where one theoretical question we will practice apart from the numerical questions. So the question 1 of the tutorial is actually about centrifugal compressors, to test you whether you have remembered and understood the theory correctly. The question is, maximum operating flow rate through centrifugal compressor at a given RPM. Yes, this is one of the GATE questions. Limited. Stall. Now, it is talking about stall of impeller blade, right? Any compressor which may be axial or centrifugal is always going to have some operating flow rate, m dot, right? And this question at any point may come like this. You should not be surprised. That's the reason why I'm bringing this question and giving the theoretical understanding, right? This motion may be centrifugally directing the streamlines like this, or may be axial. The whole point about m dot, which is rho AV, right, is that a stall in impeller blade, what will it do? A stall in impeller blade would cause these impeller blades here to not transmit the energy, to the fluid. So in that stall region, the delta V imparted would go down. The compressibility will be reduced. So mass flow rate will come down. But is it maximum? Does it govern maximum? Stall happens at some percentage of blade. Not entire blade can stall, right? We have seen these angles. It's twisted. Even if it is stalled at most of the sections, some sections will never stall. Obviously not. If you understand a centrifugal compressor surge, obviously not. Inlet flow distortion. This is the blade, may it be of axial or centrifugal. The flow is getting directed at certain angle, theta or beta. Distortion would cause certain non-optimum energy transfer. But again, this is not the driver. Distorted flow would produce lower specific work, but not minimum operating condition. Because at a given RPM, most important, this distortion would reduce it, not significant. Moment M diffuser becomes 1. No matter how great optimization you do on these and this, you cannot move anything further. Because of the compression diffusion choking, you cannot do more mass flow. Very, very important concept which you should be extremely clear about. So this tells me that the operating mass flow rate is governed by the throat design of the diffuser. And that is the most important implication for a blade design person. Okay, that's question number 1. We will now go to question number 2. A jet engine is operating at a Mach number of 0.8 at altitude 10 kilometers. Okay. Efficiency of the intake, eta intake is 0.8 and eta compressor is 0.87. So this is given. So some guy has done already the complicated cycle analysis and has provided us these numbers. Total temperature at the exit of air inlet and compressor would be, and we have been given P infinity 2603 kPa at 10 kilometers, T infinity 223 Kelvin, gamma 1.4, rho and pi RC, and pi is 8. So some guy has designed the blades going through the theory of how the blade stalls, surge and so on with these numbers. He has also given us the efficiencies as measured. Now, first and foremost, T01 at diffuser is assumed through isentropic flow, equations of engine analysis. Diffuser in isentropic flow would slow down the flow with this, clear? So, if I substitute the numbers, .2 times 0.8, right? 1.4 minus 1 is 0.4, by 2 is 0.2. 0.8 square is 0.64 times T infinity, which is 223. We have already taken it here, right? So this is 1.128. On multiplication, you would get this 251 Kelvin. This is the diffuser exit and inlet of the compressor. There is hardly a loss in between. The staging is assumed to be smooth. So we got one answer. Now, in the compressor, what is the relation? T03 upon T01 is equal to 1 plus 1 upon eta C pi C raised to gamma minus 1 by gamma minus 1. How did I arrive at this relation? Let me write one step behind. Pi C raised to gamma minus 1. This is T03 dash upon T01 minus 1, which means right? But this is what we know. See what I have done? I have, for you, re-walked all the steps of eta C pi C relation from engine, so that you are very clear. How is the efficiency defined? Right? I have walked you through how the efficiency is defined, which means based on this relation, I will substitute and get T03 as T01 1 plus pi C raised to gamma minus 1 by gamma minus 1 upon eta C. Now I can substitute 251. Where did this appear? In T01. Right? I made eta into m square, the efficiency part. That's why I was getting the lower number. Otherwise I would have got isentropic flow. What is pi c? 8 raised to 0.4, which is 2 by 7 minus 1 upon 0.87. You can very quickly substitute this in your scientific calculator to get 486 Kelvin. Now see the rise in temperature. That is important to analyze. Compressors for pi 8 is giving you tau of about 2. Which means higher the compression, more will be temperature rise. Now this 400 Kelvin flow, hot flow, is going to enter my combustion chamber. Fuel is added, turbine is rotated through this, nozzle expands, and that's how the components match. As an undergraduate student of propulsion, you should have these concepts very, very clear in your head. How each of the component talks to other component. Okay? Question number 3. Air at a stagnation temperature of 15 degrees Celsius and stagnation pressure of 100 kilopascal enters an axial compressor with absolute velocity of 120 meter per second. I already know this. They have given me 15 degrees Celsius as stagnation and stagnation pressure as 100, which means if I reduce everything to 0, okay? C, what is C1? 120 meter per second. Absolute, right? Absolute frame of reference. Inlet guide vanes directed to the rotor at angle 18 degree. Immediately I should translate the information like this. So there is an inlet guide vane which directs it, right? Rotor turning angle is 27 degree and rotor blade speed is 200 meter per second mean. We have seen this is going to change from root to tip, hub to tip. It is varying, so it is an average that we take. Remember our diffuser efficiency D because of this, and remember our work done factor lambda because of omega r being root to tip different. That's why mean is coming. See how things relate. Axial velocity is assumed to be constant. Undergraduate assumption again. Fair enough assumption. If mass flow rate is 1 kg per second, the power required to drive the compressor is, this is one of the GATE questions. So we have been asked power requirement. Work done or power is m dot into u into c theta 2 minus c theta 1. Immediately I wrote this formula. How? Momentum change into rotational speed. Do I have this? Yes. Do I have this? Yes. What don't I have? This, which means I need to find this. Now absolute component is given. I also know that this c theta 2 minus c theta 1 can be written as cz tan beta 1 minus tan beta 2. I also know phi, which is beta 2 minus beta 1 is 28 degrees. It is rotating the flow through this relative angle. What is Cz? C cos alpha, cos of 18 degree. So this is 120 into cos of 18 degree. If you do this on your calculators, you would get this as 114.2 meter per second. So I know the axial velocity, Cz. Now, the turning angle is 28, right? beta 1 is 55. What would be beta 2? 28 degrees Celsius. Right? I'm sorry, I'm so sorry. This is how the mathematical arithmetic errors may happen. We have been given the turning angle with respect to the blade, the design of 27, which means beta 1 minus beta 2 is 27. Given the beta 1, your beta 2 is 28. So, since the information provided to you tells me the beta 1s and beta 2s, I can now substitute this like this. Into 200 into 1, right? M dot U Cz tan beta 1 minus tan beta 2. This you get as 20.46 kilowatt. So this particular compressor would require 20.5 kilowatt power to be extracted from turbine to do these operations. The next part of this question which they had asked was, given this power information, okay, given this power information and assuming eta of 1, impossible but theoretically, find out the pi c. Now, such a question you should never get confused as to what did I learn, what did I forget. This you have to attempt it very, very calmly. We know that eta c and pi c are related in a very, very simple way. What is the relation? Pi c is 1 plus eta c u cz upon cp t01 tan beta 1 minus tan beta 2 whole raised to gamma by gamma minus 1. Right? Air is given 1.4, we can assume safely. T01 is given 273 plus 15, 288. Cp of air is 1004, right? 1 point something. This is 1, which means this is 200 into 114.25, right? We have already computed this number in terms of kilowatt, right? So whole thing you have to do is substitute it here. 20.46 into 10 raised to 3. If you forget Cp, how would you do? Gamma r by gamma minus 1. 1.4 by 0.4, which is 7 by 2 into 288. Approximately the constant, right? Or 300. So this becomes around 1005 into 288. Raised to sorry. Sorry. Excuse me. Now this is a simplification game to give you ballpark range. This is about 0.1. So this becomes 1.1 raised to 3.5. This would approximately give you 6. Which means for this given compressor with these parameters and this turning angle, the compression ratio achieved P03 to P01 is 6. And so P03 you would get at stagnation is 600 kP. That was the another question. Okay. So this is a very close question. It's an extremely close question, as we say, right? Question number 5. The inlet stagnation temperature of a single axial compressor is 300 Kelvin. What does single mean? Only one stage, rotor stator. Undergraduate simplification. Series of blades are not considered. So T01 is 300. Stage efficiency is 0.8. blade speed is 200 meter per second, axial flow velocity is 160 meter per second, inlet relative blade angle is 44, outlet relative blade angle is 40. So we have been provided ample information. Cp 1005, gamma 1.4. What is the pi c? This is just the extension of the previous question, by the way, and this was in one of the another GATE exam. So this is one of the favorite topics to ask. Now, what is T03 minus T01? U Cz tan beta 1 minus tan beta 2. This is Cz axial upon Cp. Therefore, if you substitute this, what will be the delta T? 22.8. That means what is T03? 322.8 Kelvin. You just have to substitute these numbers. 200 into 160 upon 1005, tan of 44 minus tan of T. And that is not equal to tan of 30. Please don't make that arithmetic error. Now, pi c is related with how? 1 plus eta c T03 minus T01 upon T01, right? This minus 1 raised to gamma by gamma minus 1. So this is 22.8 upon 300. Eta c is 0.8. If you now substitute this, you would get 1.23. So the pressure ratio achieved is 1.23. You may feel this is very, very low and your observation is very correct. Now we have to guess ourselves why. This is not asked in any questions, but this is your own introspection to get more flavor. We said blade speed is 200 meter per second, which is quite high. Right? It's a decent enough velocity, right? If typical radius is say 0.1 meter, omega is 200 rad per seconds, right? How do you convert rad per second into RPM? Pi radians is 1 rotation. So 200 radians is x rotation. So 200 upon pi into 60 RPM, right? This you can simplify. So it's about 4000 RPM. And 10 centimeter radius, which is typically the blade height, right? 10 centimeters, which means the speed is very, very high. It is single stator rotor combination that makes the difference. The Cz that you saw was 160, very high axial velocity. So just by having one stage is not enough. These 22 have to build up to give you 200 to 300 degrees Celsius rise to get sensible pi c, right? Now you get the importance of spooling. Now you get the importance of multi-stage. This question introspectively will tell you this answer. As an undergraduate student, please build this appetite to see beyond the numbers. Very important. Sixth question. For a multi-stage axial compressor with constant hub diameter. So multi-stage axial compressor, our hub is constant. What does that mean? We had seen one picture here, right? I'm just exaggerating. Where hub radius was increasing as you moved downstream. Now we are saying that is not the case. Hub radius is constant. What would happen? Blade height decreases in flow direction. Blade height increases in flow direction, remains constant, or first increases, then decreases. And this is again one of the very, very important GATE questions. If you remember my lecture, we had said you make hub progressively going up and the clearance between hub and tip smaller, 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 because as the pressure keeps building up, density moving up, rho A V, V is almost similar, relative velocity is not changing much. Area has to constrain to maintain the mass flow. Mass flow rate within the stage cannot change, right? M dot is conserved. M dot here before, just at the beginning of compression, is where the full compression is achieved. But look at the density change. So you have to reduce the area. Now hub is constant. Only ways decreasing. If you keep increasing, more work will be imparted. More work means more density. More density means more mass flow. This is abrupt. Why? W by m dot cannot change sign. Transfer of work has to be smooth and continuous because this is directionally asymmetric. See the mathematical reasoning. So increasing, decreasing function will not satisfy just case. It has to be monotonous function. Right? That's the reasoning I am doing. Physically, I cannot keep adding some energy and then removing some energy relatively. I have to always incrementally add some energy, or increment should be zero. I cannot start removing the energy from the fluid. Moment this happens, to balance the mass flow, you will have to extract the energy. Now you cannot have half blades rotating in positive direction and half in negative, right? Whole point of compressor is gone. So this question tests your theory of axial compressors and velocity diagrams. The last question of this tutorial is going to be now on something interesting. Okay? So let's practice the last question. And I'm trying to find a great question. Okay. Question number 7 is very, very good. If no IGV are present in compressor, can it be used as turbine as well? IGV is a very peculiar property that we saw only in compressor, never in turbine. Why? The fluid which came out of combustion chamber rotated in the velocity diagram the turbine first. So rotational blades were directly rotated in compressor, not in turbine. Turbine had diffuser to reduce their energy before they can face a rotating component. Inlet guide vanes are used in compressor because the diffuser section, which is providing you diffused flow in the reduced velocity, has to guide to the blade angle. That's why IGVs are important. Alpha 1 not equal to 0 is the criterion we are using. If there are no IGVs, you would see rotor, stator, combination. If I flip and go on other side, what do I see? Stator, rotor, stator, rotor, stator, rotor. If the design is with the constant hub radius, answer is yes. Rotate the flow direction. Just reverse it. Theoretically, nothing from fluids engineering or propulsion engineering stops you from doing this. If IGVs are not present, this acts as a compressor and compresses the flow, or this acts as a turbine and expands the flow. Imparting energy, compressing it, extracting energy, expanding it. Mechanically, there are of course a set of challenges. Something called as turbine compressor matching through spools. The hub radius which increases here would not allow your turbines in a small concentrated zone to operate with such a high temperature. So material science guy there and mechanical engineer guy there will not let you do, but propulsion engineering can let you do. So this is a very, very good question to understand the nitty-gritties of axial compressor. This closes our tutorial on axial compressors based on the velocity triangle diagrams and a theoretical understanding of compressors. Thank you.